Hello, let's start with the seminar 5 of the course Linear Dynamical Systems. I am gil.astudillo. I am going to talk about some shadowing properties. I prepared these tests that you are seeing now. Well, these tests have a detailed explanation of the main parts of the theorems A and B of the paper of Bernardes, Cirilo, Darji, Messaoudi, and Pujals. The title is Expansivity and Shadowing in Linear Dynamics of the Journal of Mathematical Analysis and Applications. I said here the main parts because I am not going to prove the exact theorems, okay? But I am going to prove the essence of both theorems. Okay, so let's see the goals. The first goal is to show that hyperbolic generalized operators have the shadowing property theorem A, and the second goal is to show that exists non-hyperbolic operator exists a non-hyperbolic operator with the shadowing property. Okay, well, let's talk about some preliminaries. Definition 1. Given a metric space and a homeomorphism H from n to m, recall that xn, that a sequence xn is a delta pseudo trajectory of H for delta greater than 0 if the distance from H xn to xn plus 1 is less or equal than delta for all n in C. Okay, H had the shadowing property if for every epsilon greater than 0 there is a delta greater than 0, such that every delta pseudo trajectory xn of H is epsilon shadowed by a real trajectory of H, that is, there is x and in m such that the distance from xn to hn of x is less than epsilon for all n in C. Well, this is saying that the sequence xn and the trajectory of x, they are going together, okay, in a distance of epsilon. Okay, given a Banach space X by an operator on X, we mean a bounded linear map T from X to X. Okay, definition 2. Let T from X to X be an operator on a norm complex space X. The spectrum sigma T of T is the set of lambda in lambda of complex numbers such that the operator T minus lambda identity is not invertible. The spectral radius of T is the supremum of the absolute value of the lambda in the spectrum. Okay, you take the absolute value of all the lambda in the spectrum and you take the supremum of that, and it will be the spectrum values, and this is denoted by RT. Okay, the spectral radius formula asserts that RT is equal to the limit of the norm of Tn to the 1 over n when n goes to infinite. Okay, if x is equal to LP C for p greater or equal than 1 and infinite, or x equal to C0, then we define the forward shift and the backward shift, this and this one, given by this definition. Okay, you go forward and and, and multiply by the weight. Okay, so these are the bilateral weighted forward, this one the F, and backward the B. Okay, where W is the sequence of bounded scalars. It's a sequence. Okay, to define these two operators and it is called a weight sequence. It is like a weight. Okay, you multiply by the weight every coordinate. Okay, okay, recall that FW and BW is invertible if you have that the sequence is separated from zero. You have a separation. Okay, the infimum of the absolute value of the sequence of weight is greater than zero. This is a mistake here. This is a mistake. Okay, I need to erase that, but I am not to pause here. Okay, well, definition 3, an operator T is said to be hyperbolic if the spectrum of T, that if the intersection of the spectrum with the sphere of radius 1 centered at 0 is equal to the empty set. Okay, now the steps that we are going to take in order to conclude the seminar will be: the first one, prove the key lemma. The second one, well, I will say what is the key lemma. Okay, the second step will be to prove the theorem A using the key lemma and the spectral radius formula, and the third step will be prove the theorem B using the theorem A. Okay, the key lemma is just a name that I put to one lemma. Okay, is this lemma here. Okay, the lemma says an invertible operator T on a Banach space X has the shadowing property if and only if there is a constant k greater than 0, such that for every bounded sequence Cn in X there is a sequence Yn in X such that this happens. You have the supremum of the norm of the sequence of Yn less than or equal to k times the supremum of the norm of the Cn. Okay, and you have this equality here for all n in C. Okay, you see that this characterize all the operators T on a Banach space that has the Chadwick property. Okay, to prove the theorem A, we need only the converse direction. Okay, from here to the Chadwick property. Okay, remember that the theorem A says almost that, well, says something like that. Okay, that the hyperbolic generalized operators have the shadowing property. Okay, so we are going to use the converse of the key lemma. We are going to prove that the hyperbolic generalized operators have this property. Okay, so they will have the shadowing property by the lemma. Okay, in the test I prove the I prove both directions. Okay, but I am going to talk only about, in this presentation, only about the converse direction. Okay, but because we only need that. Okay, is here, sorry, is here the converse. I'm going to put the lemma here. Wait a minute. Okay, so we have the lemma here and the converse. So okay, we have here, for the converse, consider epsilon greater than 0 and put delta equal to epsilon over 2k, and let a sequence xn be a delta be pseudo trajectory of t. Okay, and put Cn equal to xn plus 1 minus t of xn. Okay, look at this. You have a sequence xn that is a delta pseudo trajectory. Okay, and you define the Cn. This is an arbitrary delta pseudo trajectory of t. Okay, and you define this. Remember that we are going to prove that the operator t have the shadowing property. So in the final steps, we want a point that that epsilon shadow this orbit, this sequence. Okay, so by hypothesis, there exists a sequence ym such that 1 and 2 holds of the lemma. Okay, remember that we are doing the converse direction. So okay, well, we have to note here, to observe here, that the sequence Cn it is bounded. Because why? Well, because it is a delta pseudo trajectory, and if you put the norm here, you will have that this is less than or equal to delta. Okay, you put the norm here and here, you will have that the sequence Cn is bounded. So by the lemma you have that exists a sequence yn that satisfies 1 and 2. Okay, now we have this. Since x n plus 1 minus y n plus 1 is equal to t of xn minus yn, it follows that this, well, you see that there are two colors, no? There is the black color and the blue color. The blue color are some details that I am feeling that are not in the paper. Okay, but we can see this because of the blue color. So you have this xn minus 1 minus yn plus 1, sorry, xn plus 1 minus yn plus 1, you have this here, is equal to, you use this definition of Cn, you put it here, and you use this the property 2 of the lemma, the condition 2 of the lemma, yn plus 1 is equal to this. Okay, you can see it in the lemma above. Okay, you make the substitution here, and you have this Cn with minus Cn, you can cancel that, and you have txn minus yn. Okay, so this is true. Then it follows that from this it follows this, and why? Well, to see this, consider an auxiliary sequence wn with wn equals to xn minus yn for all n in C. You can see that because of this, you will have that wn plus 1 is equal to t of wn. So it is like a chain. Okay, you have one element of the sequence, and the next one is the t of the previous element. So it is an orbit. Okay, this happens for all n in C. So the sequence wn are the forward and backward iterations of w0, that is, the sequence of the whole orbit points Tn w0. So this sequence wn is the same as this. That's why this is true. It's the same. Okay, so you can put x equal to x0 minus y0, and you will have this xn. Okay, making the substitution here, you have this, you put this here. Okay, and then you use this here, and you have this, and it's equal to yn. Okay, then you see that the norm of xn minus tn of x is equal to the norm of yn from this equality, that is less than or equal to this for the property 1, for the property 1 of the lemma, the hypothesis, okay, and this is less than k times delta. Remember, let me show you. Remember the definition of Cn, okay? The norm of this is less than delta. So you have here, oh sorry, here. So you have here that this sequence, you have this inequality, okay, from the lemma. And this is delta, the supremum of Cj is less than delta, okay, less than or equal to delta, and we take delta equal to here epsilon divided by 2k. So you have here this that is less than epsilon for all n in C. So we have what we want. We have what we want, okay? So the converse is 2. Okay. Let's see now the theorem A and his proof. Okay. Let T be an invertible operator on a Banach space X. Suppose that you have a decomposition. You have X equal to M direct sum N, where M and N are closed subspaces of X with T of M contained in M and T minus 1 of N contained in M. If the spectrum of T restricted to M is contained in the unitary disk and the spectrum of T minus 1 restricted to N is contained in the unitary disk, then T has the shadowing property. Okay, we are going to use the key lemma that I called. So we are going to prove that an operator with these properties 1 and 2 that satisfies these properties. Sorry, we are going to take an operator T with all of these conditions, and we are going to show that satisfies the second part of the lemma, okay. Okay, well, let's start the proof. Okay, for each x in X, take x1 in M and x2 in N, satisfying this. Okay, x1 and x2 are unique because it is a direct sum. Okay, there is a constant b beta greater than 0 such that this happens. The norm of x1 is less than or equal to beta of the norm times the norm of x, and the norm of x2 is less than or equal to beta times the norm of x for all x in X. Why this is true? Well, remember that I am using the the blue color to fill the details of the paper. Well, to see this, or at least this was not clear for me, okay? So that's why I am going to show how to get this beta. To see the existence of this beta, consider the function L from this space m times n to x, defined by L a b equal to a plus b. Since x is the direct sum of m plus n, L is a bijection and it is linear because of his definition, okay? Putting the induced norm on M and N, we have that M and N are both Banach spaces because they are closed subspaces of X, okay? Then the product N times N with this norm is also a Banach space. Okay. To see that L is continuous, take a sequence an bn such that goes to 0. Then you have this we are going we are proving some properties of the operator T to use the open mapping theorem, okay? To use the theorem we need to show that L is continuous, so we are showing this. Well, you compute the norm of this L of an bn is equal to this, and the inequality, I don't remember the name. I forgot the name of this. A triangle inequality, you have this is less than or equal to 2 times the maximum of I make a mistake here. You need to put here an and bn, okay? This is equal to 2 times the norm of this, that is equal to this. Remember that you need, I make a mistake here, this is an and bn, okay? And this go to 0, so you have that since L is linear, this shows that L is continuous, okay? Remember that for a linear operator you need only to show the continuity at 0 to show that it is continuous, okay? Because it is linear. So applying the open mapping theorem for Banach spaces, we have that L minus 1 is also continuous. So there exists a beta greater than 0 such that this happens, okay? This happens for the continuity, but this is equal to this and this is equal to this, so we have what we want here, okay? Let's see, if you take an x in this way, an x with x1 in m and x2 in n, you will have this because of this. Look at this here, the left side and this left. Oh, I make another mistake here. We need a beta here and here. I'm going to write here to correct the test. Okay. Okay, we need here beta and beta. Thus, the existence of beta is guaranteed because of this, okay? We have this beta that we need to prove the theorem A. So let's continue. By hypothesis, the spectral radius of T restricted to M is less than 1 and the spectral radius of T minus 1 restricted to N is less than 1. So choose T in R such that this happens. This is easy because both are less than 1. You choose T that this happens, okay? This doesn't have any problem, okay? It follows that from the spectral radius formula that there exists a constant C greater than or equal to 1 such that this happens. The norm of T restricted to M to the N is less than or equal to C times T to the N, and this similarly to T minus 1, okay, for all N in N0. Okay, this property. How? Okay. So now, why can we choose a constant C like that? Well, by the spectral radius formula, but how? Suppose that you have this, that the spectral radius of T restricted to M is equal to S, and choose epsilon equal to T minus X greater than 0. This is greater than 0 because remember this T is greater than this number, than R, than the spectral radius of T restricted to M. So you have a difference greater than 0, okay? So applying the spectral radius formula or using the spectral radius formula, there is N in N such that if N is greater to N, you will have this. Okay, remember that the spectral radius formula asserts that this, so you have that this in the limit go to S. If you put an epsilon, you will have that for some N that there exists N in N such that there exists a capital N in N such that N, if N is greater than capital N, you will have this situation here, okay? Only by the limit, just by the limit. You will have this, remember S is the limit, so you take you take S plus epsilon and you have this, but this is equal to T, so when you take the power n to both sides, you have this, okay? You can think that this is the the constant 1 that you want. Okay, you can put here c equal to 1, but this happens only to n greater to n, so you have to solve that. But we, we can choose easily constants c0 to cn such that this happens for k from 0 to n. So you can control a a finite by finite elements. Okay, so you can control this, and you can control the tail, so you are done. You can put c1 equal to the maximum of this set, and this constant c1 satisfy this for all n in n0. Okay, why you can choose this constant? This is easy because tk is greater than 0, so you can put ck greater than this divided by tk. There is no problem. So you can have this c1 and you solve this for t restricted to n. Then in the same way you solve this to t minus 1, you will have a c2, and you have and you take the maximum. Okay, as I said here, you put this, and you have this condition. I make a mistake here. This is c1, and the same way you obtain c2, and you take the maximum, and we get the constant c desired. Okay, let's continue. Remember, the blue letter are the details that I am filling, and the black letter, the black words, and the black words is the paper, and the blue words is the details that I am filling. So continue. Let's continue here. Consider a bounded sequence Cn in X. For each n in C, we define this. This is a tick. Okay, but you have a construction here. Remember that you wanna have this side of the lemma, the 1 and 2 condition. You want to construct a sequence yn. Okay, you are seeing here. Okay, remember where we wanna go. Let me just, I get lost too, so I imagine that you do. So at the beginning we separated here, we prove this property. This is very important, that this work for all x in X. Okay, that this property work for all x in X. This is very important. And then we make this, okay, this property, okay, here we enter in the condition of the lemma. Remember, we need to consider a bounded sequence Cn, okay, and prove that there exists a sequence Yn with some properties, with the properties 1 and 2, okay, with the conditions that satisfies the conditions 1 and 2, okay. So we have the Cn sequence, and we are going to construct the Yn sequence, okay, that satisfies 1 and 2. Okay, so let's continue here. We define the sequence Yn in this way, Yn1 plus Yn2, where Yn1 is equal to this, the sum from k equals to 0 to infinite of tk of this C1 of C n minus k minus k minus 1, the first part, and you can see that this is in M because Tm is contained in M, and you have also this definition here. See that this starts from 0 and this from 1. You have the difference here, and you have a minus here, and the inverse of t, because you have other property here. Let me show you the theorem A. You have t minus 1 of n is contained in n, so you use this, okay, and this is in n. Okay, you define this, then the paper says that an easy computation shows that 2 holds. In fact, is it an easy computation? But we are filling the details, so I'm going to show that the condition 2 holds. The condition 2 of the lemma. Let me show you the lemma again. You can see the condition that is this, okay, for all n in C. So it's the same this, okay. I'm going to erase the lemma. So let's continue. Doing the computations, we have let me show you above. Okay, we have this. You only need to put n plus 1 here and here, so you will have n minus k here and here. When you put n plus 1 here, you will have n plus k. Okay, remember that yn plus 1 will be the first part plus the second part, so you will have this, okay. And t of yn is almost the same thing, but here you apply t and you will have t k plus 1, and here you apply t, you will have t minus k plus 1, and the rest stay equal, okay. And Cn I divided here in the first part and the second part, okay, easy, okay. Here you can see that you can put here k plus 1, okay, this k plus 1, but here you can put minus k plus 1, so you have the same variation here above and below. Okay, in this part here you also have the same situation. You can put minus k minus 1, and below in the c you can put the same term here. Okay, we make this to change the sum, so you can start here when k is equal to 0, this is equal to 1, so you start here from 1, you go to infinite, and in the same way when k is equal to 1, you start here from 0, so you make this. And what do you do with this? Well, you complete this with this, and well, look that the first term, the 0 term of this sum is this, so you pick this term and you put it here, and you have this part. Okay, and when you take this and you sum with this, you will cancel the first term. Okay, because this is negative, so you will have this from starting from 1. Okay, so you see that this t of yn plus cn is equal to yn plus 1. This is what we wanted to see. Remember here, this is the second condition of the lemma. Okay, second condition of the lemma is just a computation. Okay, continuing with the paper, it says, moreover, we have this. Okay, we have this, hence this happens. Well, wait a minute, what is this? Well, remember that, oh, I have a problem here, I cannot show this in the same screen, but remember that yn, the first part, is equal to this, but we have this property, so you can, when you take the norm here, you can obtain a c here, tk, and the norm of this. In the same way, you have, when you put the norm here, you take, you will have the ac and a tk and the norm of this term. Okay, that's why this happens. You have the c, tk, and the norm of the term. You can see again here, when you take the norm of this will happen, and in the same way this will happen here. Okay, so you get these inequalities. Okay, from here, hence we have this, the supremum of the norm of the yn is less than this times the supremum of cn. This is the first condition of the lemma. You have the supremum of ym well, the first condition of the lemma. Okay, this is the key. The key. Okay, so we only need to prove that in order to show that the operator t is hyperbolic, because we take a bounded sequence Cn, and we construct a sequence Yn that satisfies 1 and 2. Okay, so we only need to show now this. And why this happens? Well, the norm of Yn is equal to this by definition, and this is less than or equal to this by the triangle inequality. There is missing a parenthesis. There is missing a parenthesis here and here, here and here. Okay, and this is okay, you are seeing this right, but I need to erase this. Okay, so you can see better. Okay, this is less than or equal to this. Okay, yeah, this is less than or equal to these two terms here. Okay, there is no problem. Okay, okay, I add a zero term only to be able to add the two sequences without any problems. Okay, but these are positive terms, so there is no problem. So you take out the c, and then you apply the first inequality that we get. Remember, you can controlate the first part and the second part with a beta. This where it is, this inequality, you can control the first part with a beta and the second part with a beta 2. So you have this. You can change the first part for the whole number, for the whole, yeah, this is a number. Okay, so you have this, and then this is, you can change this by the sub of the sequence, so you have two times the supremo. Okay, and you have the sum, the arithmetric or geometric sum, isn't it? I'm not sure now, but you know that these converge to this number, so you have the inequality. And finally, we get that the theorem A is proved. So, well, this proves that T has the Chadwick property by the key lemma. Remember the lemma. We prove both conditions giving a bounded sequence. There exists a sequence Yn. We construct all of this here, so we get that we got that T has the Chadwick property. Okay. Okay, now we are going to prove the theorem B using the theorem A. Well, let X equal to LQ of C with Q, greater or greater than or equal to 1, and finite, or x equal to c0, there exists an invertible weighted shift t on x which has the shadowing property and is not hyperbolic. Well, we are going to show that there is an operator t in these spaces in a space like that satisfies the conditions of the theorem A that you are seeing here. That is, we're going to show that x have the composition into spaces M and into subspaces, into closest subspaces of x, M and N, that x can be written as a direct sum of M plus N. Okay, and you have all the other properties, that T of M is contained in M and T minus N is contained in N. Okay, and the properties of the spectrum also, and it will have the shadowing property. Okay, consider let's prove the theorem B. Fix a real number alpha greater than 1 and let t be the bilateral weighted forward shift on x whose weight sequence is this, given by Wn equal to alpha if n is less than 0 and Wn equal to 1 divided by alpha if n is greater than or equal to 0. By applying theorem A with this set M and this set M, these subspaces with these subspaces of x, we see that T has all the above mentioned shadowing properties. Well, this is a mistake that I make here writing, because we have only here one shadowing property, but in the paper we have another shadowing properties. There is the LP shadowing property and the limit shadowing property that I am not using here. Okay, that's why I made this mistake, but there is only one shadowing property that we prove. Okay, so okay, let's see that T satisfies these requirements that I set of the theorem A. First of all, we have that this happens. M and N are close to the spaces of X. Well, I forgot to, to tell something about T of N contained in M, but you can see that the forward shift you have the negative coordinates equal to 0. So when you apply the forward shift is contained in M, and in the same way the positive coordinates are equal to 0. So when you apply the inverse of t, it is a backward shift, then you have that the positive coordinates are equal to 0, so there are invariants. Okay, by m is invariant by t, and n is invariant by t minus 1. Okay. Okay. We have this sum x equal to n direct sum n. They are closed subspaces. It's easy to see. If you take a sequence in M and a limit that is going to a limit in X, you will have that the limit must be in M. Okay. So okay, you have this when X equal to this. Okay. No, let me erase the lemma A, the theorem A. Okay. Okay, we have that t is a forward shift, so it is defined by this. To be more easy to see, I put this way. I put a hat on the 0 coordinate, so you have the hat, and this is a shift forward of a forward shift. Okay, but with the weight sequence. Okay. So this is t, and t minus 1 is this. So you can see here that the sequence change the side, the weight, the sequence of weight of the weights change the side. Okay. Now looking at this, you can see that if you take x in M, you will have, when you apply t, to an x that is in M, remember that the negative coordinates are 0, so you can put these all zeros, and you will have from x0, when you apply t, you will stay here, and there will be a contraction, so you will have this equality. And in the same way, when you apply this, in the same way, if x is in no, that's right. Okay, in the same way, when you apply k times, you will have 1 over alpha, 1 over alpha, 1 over alpha, k times. So you will have this for all k in N. This implies that this inequality, okay, because you have this for all x, so you will have this equality for all k in N. Then by the spectral radius formula, remember that it is this formula, you apply this formula, and you will have that the spectral radius of t restricted to M is equal to alpha. Okay. Oh, I make a mistake here. 1 over alpha, that is less than 1. Okay, it's less than 1. We need less than 1, so 1 over alpha is less than 1. Similarly, you make the same thing, and you can compute. Look at this. When you take an x in N, you will have that this is 0, so you will state in the left side and you will be multiplying by 1 over alpha. So this is the same computation. You have this, and by the spectral radius formula I make the same mistake because I copy and paste here. So this is 1 over alpha, okay? Is less than 1. Okay. Okay. So with this we have that T has the shadowing property, okay? Because we prove all the conditions of the theorem A. Remember this. M and N are closest to the spaces of X. With all the conditions, we have proved that. So T is has the shadowing property. Now we want to prove that that T is not an hyperbolic operator, okay? uh, that is what is saying the theorem B. We show that T has a shadowing property, but now we want to show that is not hyperbolic. To see that T is not hyperbolic is sufficient to show that there is a non-trivial fixed point. You can see that the sequence xn defined by this is a fixed point. Then 1 is in the spectrum, thus T is not hyperbolic because the spectrum will intersect the unitary sphere, so it will not be hyperbolic, okay? Why this is a fixed point? Because remember, to see that this sequence is a fixed point, you see that when you apply T, you have this part and you divide it by you multiply it by 1 over alpha and make the shift to the to the to the right side, okay, to the right. When you multiply this by 1 over alpha and make the shift to the right, you have this same part, okay? And when you have this part multiplied by alpha and make the shift to the right, you will have this, okay? So it is a fixed point. Okay, you can ask, okay, but why this sequence is in the space X? Well, you can compute its norm, and you can see that this then the LP norm, you can see this, okay? And there is no any problem because this is a geometrical sequence. Okay, there is no problem. Geometric sequence, series. Okay, and this is finite, so X is in X, and that's all. We have shown that the theorem B is satisfied, okay, for this operator. Okay, that's all. Thank you.